Hello friends, we are back with our series of webinar under the umbrella of Igniting Power Engineers. And I should say thank to everyone for your support, and we are back only because of your support. Before I start and I invite the presenter of today's, I would like to thank Almighty, my friends, my mentors, my friends, my good wishers, and because I personally believe without these people, this journey wouldn't have been possible. A few names include respected Bhai sir, KK Murthy sir, S. Apao sir, KK Gupta ji, SK Batra ji, Vishwanath ji, Sanjay Agarwal ji, my friend Saket, Rakesh, Pradeep Garg, who just pushing me every day, supporting me every day. My team behind the scene, Gulab, Ramdhani, Abhishek. And now time to give a brief introduction about the today presenter. He's a very special guest, Pankaj Kumar Jha ji. He's a highly competent and proactive electrical engineering professional, having 11 years of experience of power system protection installation, testing and commissioning. He has commissioned transmission lines, reactors, transformers, busbar for 220 kV to 765 kV EHV-AC system. He is the member of protection expert group of PGCIL, and he has done protection audit of more than 40 substations across various regions of India. Presently, he is working at Mandola substations of PGCIL, and I would like to request Pankaj Jha sir, kindly share your screen and start giving your presentation on the fundamentals of protection system. We all are eagerly waiting for that. Sir, kindly unmute yourself. You are muted.
Thank you, sir. Am I audible?
Kindly start.
Okay. Thank you, sir. First of all, for this.
Pankaj, sir, I think you have logged in from two systems. That's why the echo is there.
Sir, you have logged with the two systems. This is the reason. Kindly log out one system.
Is it okay now?
So now you unmute, it will work.
Okay. Thank you again. And first of all, sir, thank you for giving me this opportunity to present my session on fundamentals of power system protection. I will directly start with my session without wasting any time. And as you can see, is this PPT visible?
Yes, sir.
Sir, it is visible. Kindly continue. And I request all the participants to kindly note down the question, whatever comes in your mind. At the end of the session, we will take all the questions one by one.
Today we are going to discuss about the fundamental concepts of power system protection. And in this webinar, I will try to cover these topics, especially the concept, the fundamental concepts of power system protection, followed by the concepts of transmission line protection, then the concepts of ICT, reactor, busbar, LBB protections, finally auto reclose and some ancillary protection functions. So first of all, some of the basic functions or some of the basics of power system protection. And this is a very basic slide. You can see whenever a power is generated, it is already much far away from the actual load centers, and this power generated at the generating stations need to be transferred through various devices like the transformers, then the transmission lines, then the step down transformer, and so on, and it will be connected to the national grid, regional grid, and local grids. But the important thing that we can see over here is that all of these portions, that is, whether it is national grid, regional grid, local grid, or at the end the consumers, everything is exposed to the environment. And so always there are a chance of uh, failure, chances of fault on this system. So we are going to discuss about those scenarios in which there are chances of fault either on the transmission line, on transformers, on reactors, or at the bus bar levels. And finally, how to isolate those faults. These all things will be discussed in today's session. So this is a very basic definition that has been taken from the book Art and Science of Protective Relays. And if you see the function of protective relaying, it is to cause the prompt removal from service of an element of a power system when it suffers a short circuit or when it starts to operate in any abnormal manner. So we have to isolate a part of system whenever it suffers a short circuit or whenever it starts to operate in any abnormal manner. So what are the normal operations? Basically, a normal operation means no failure of any equipment, no mistakes from any personnel, and no act of God. But all these things cannot be true at any given point of time. Uh, Especially for the Indian power sector, when we have the attendance, the manual attendance for the operation, as well as the aging equipment, widening gap of supply and demand, along with the seasonal variations. So there are always a chance of high faults in chances of more and more number of faults in our system, and we have to understand each and every types of faults, and then only we can decide which types of protections will be suited for which types of faults on the network. So what are the requirements of the power systems? We know that faults are inevitable in a power system and it may risk to the life or property disruption in power supply. Uh, at the same time, a power system fault must be cleared as fast as possible. So this is a very important thing for us. A power system fault must be cleared as fast as possible. And why we need to clear the fault as fast as possible? It is clear from this slide. So this is a very simple power system network in which we can see a generator followed by transformer, transmission line, and load. In normal scenario, the power will flow from the source to the load, and there will be load current. We can call it as IL. Now suppose there is any fault on this transmission line. Whenever there is a fault on this transmission line, as compared to this path. And first of all, because of this shorter path only, it is called short circuit, because your circuit.
Sir, your slides are not moving. It is you are on the very first slide.
No, I have moved to fourth slide.
No, it is not moving.
Not moving.
Go to full slide mode. That will help.
Yes, I was in full slide mode only. Just check. Is it moving now?
No, still it is not moving. Now it start moving.
But no, I have. Is it moving now?
Sir, kindly go to the full slide mode. It is not full slide.
I am already on full slide mode.
But the slides are not moving. Now it's okay. Now it's okay. It's moving.
But now it is not full slide mode.
Yeah, it is moving now.
But it is not full slide mode. Just give me 1 minute.
No issue. But now the slides are visible at least. No issue with that. Kindly continue with that one.
Okay. So actually, just 1 minute. If it is, I think in full slide mode, it is not changing. Just check. In this mode, is it changing or not?
Yes, sir. Changing. It is changing.
Changing. No? Okay. So I was actually at this slide. This first of all, sorry for the inconvenience, and this was because of some issue in my computer. So now I was on this slide, which is actually the normal operation. If you see the normal operation, actually it is in case of normal operation, it is assumed that there will be no failure of any equipment, no mistakes by any personnel who is operating the system, and no acts of God. System is capable of meeting the supply demand requirements along with certain variation in the supply load. But unfortunately, these three conditions cannot be true during all times. And especially in the context of Indian power grid or Indian power system, we have attendants who are operating the breakers or isolators in the substations. The equipments which are installed at the substations are aging. We have the wide gap of supply and demand along with seasonal variations. And also we have the abnormal stress on the infrastructure. And because of this, there are always a chance of fault on the transmission line as well as in the transformer, reactor, or the bus bars. We have to understand the nature of different types of fault. Once we understand the nature, then only we can decide which type of protection system we have to use. So now the requirements of the power system are, we know that the faults are inevitable in any power system. And whenever there is a fault, it will risk the life and the property as well as disruption in power supply. So the power system faults must be cleared as fast as possible. Why we need to clear the faults as fast as possible? If you see here, this is a general power system network in which there is a source, that is a generator, followed by transformer, transmission line, and then load. In normal conditions, the load will flow from the source to the load side, and there will be a load current. Now, if there is a fault on this transmission line, what happens? Now, this path reduces. This is a short path, and first of all, because of this shortening of the path, it is called short circuit. And now if you see, because this path is reduced, this is a shortened path, so that definitely there will be an increase in current. And if you measure any voltage at this particular point of time, if you measure the voltage at this fault location, if this is the source voltage, the voltage measured at this location will be source voltage minus the voltage drop along this path. So when the current increases, definitely the voltage drop will increase. So the voltage measured at this point will going to reduce. So the general characteristic of any short circuit fault is increase in fault current as well as the reduction in voltage. Now with the increase in fault current, if you see, the total heat generated will be I square times RT. So if even if my resistance is fixed, fault current increases, the total heating will increase. And with the increase in heating, the temperature will rise and it is going to affect the insulations. So now on which factor it is being limited? It is limited by the factor T, and T is basically the fault clearing time. So what we want this T to be as minimum as possible, and that's why all the protection systems which are designed are to be designed in such a way that this time or the fault clearing time must be minimum. Also, if you see here, there were two factors. One is the current, increase in current, and another is reduction in voltage. On the basis of these two factors, we can have different types of protection system, like the overcurrent, under voltage, or if we take the ratio of these two, then we can have the impedance, that is V by I, or admittance, that is I by V, or we can have the power flow, that is V into I. So on these two factors only, the multiple types of power system protection relays can be designed. So the elements of power system protections are relays, circuit breakers, CTs, communication channel, DC system, control cables, and then instrument transformers. The functions of protective relays are to detect, trigger, report, and monitor your power system equipment. The circuit breakers are used to interrupt the fault by isolating the faulted section, and then when the fault is isolated, it is used to reconnect the system. So we will focus only on protective relays in this session. So now this is a basic fault clearing system. So what is a basic fault clearing system? If you see the last slide, there I have stated that we have in any short circuit fault, what we have is either the increase in current or reduction in voltage. This will be at the same time, that is increase in current and reduction of voltage. Now to measure those current and voltage, we need the current transformer and voltage transformer or capacitive voltage transformer. Then you have to enter the system parameters, that is in which particular system I am protecting, that is whether it is a short line or a transmission line, transformer, reactor. So these are the settings related to the system informations like the line length, positive sequence impedance, zero sequence impedance. Then we enter these parameters to the relays. After this, relay internal processing or the relay internal processor will calculate based upon the parameters of current, voltage, and then the entered system information. And now it will issue the trip command to your circuit breakers, and some output will be assigned to the annunciation system. All the fault clearing systems are designed by taking the consideration of single failure criteria. So basically, what is single failure criteria? A single failure criteria means out of n number of systems in our protection system, out of n number of elements, if any one element fails to operate, this should not affect the fault clearing of the network. So if suppose I have 10 different components in the protection system, and out of those 10 components, one component fails because of any reason, then also my fault must be isolated. And because of that, this is the general single failure criteria. If you see, for all 400 kV and above lines, basically for as per CBIP guidelines, for all 220 kV and above lines, we will be having two protections, main one and main two. Both of these may be distance, may be differential, or can be distance or differential, but these are two different protection functions of maybe two different manufacturers. Some utility are using the relays from same manufacturer also, but generally it is preferable to use the relays from two different manufacturers so that they may have the different operating algorithm, and in case due to any reason, suppose one relay failed to operate, then the second relay may operate and isolate the fault. So if you have two relays, then what you need, two CT, one for each protection, that is main one and main two, two CVT, that is one for main one and main two. Now again, we cannot have two different CTs. We will have only one CT, and out of that CT, we will be using two different code, one code for one protection and second code for the second protection. Similarly, for CVT, two codes, one will be for the first protection and second will be for the second. Likewise, for the after the operation of main one protection, it should energize the tripping coil of the circuit breaker, and we must have two trip coils so that in case one trip coil fails to energize, or if there is any problem in this path, fault must be isolated through this path. So this is one trip coil. Trip coil 1, suppose it is energized through DC1. So if you go back one step, then you will be having this DC1 through one battery set, one with one battery charger. Similarly for second. So whenever if there is any failure in this path, your fault must be isolated through the second path, and this is called single failure criteria. Now, the important point is we have understood the concept of single failure criteria. We have understood the requirement of current and voltage transformer. We have also understood the effect of short circuit fault on current and voltage. But we must understand the effect of different types of configuration on our protection system. So what are different types of configuration? Generally, we are having two different types of configuration. One is called radial power system, in which everything is connected in a radial fashion, like your generators followed by transmission lines. It is then connected to distribution and then to load in all single lines. This is the second, which is the network or meshed power system. And this network or meshed power system is the most common type, which is prevalent in the transmission networks as well as in case of distribution networks also. So now we will see what are the effects of the network or meshed power system on fault current. So this is a simple example wherein I have considered three buses, bus 1, bus 2 and bus 3, which is fed through two generators, one connected to bus 1 and one connected to bus 3. Now, the lines connected between bus 1 and bus 2 is having this impedance. Similarly, the line connected between bus 2 and bus 3 and line connected between bus 1 and bus 3 is having these impedances, which are arbitrary. The voltage at bus 1, bus 3 are given, and then you have a networks of other elements which are connected through bus 2. Now, what are the conditions? So, suppose there is a fault on bus 2. In this case, whenever there is a fault on bus 2, so what will be the total fault current? The total fault current will be this voltage divided by the impedance of this point, and this impedance will be two impedance of 0.1 connected in parallel. So that will be my current. I'm not going in detail about these calculations, only focus on this point. Once there is a fault on this bus with all the elements in service, your fault current is 20 pu, that is 20 per unit. When we have one line under shutdown, suppose the line connected between bus 2 and bus 3 is under shutdown, and now there is a fault on bus 2. In this case, the fault current will be voltage divided by this impedance, which is 10 pu. So only because of change in certain network structure, my fault current is changing. So the other effect is, suppose there is a fault on bus 2. What happens? Whenever there is a fault on bus 2, all the elements connected to this bus 2 are going to be isolated because this is connected in radial fashion. Now consider one case in which these networks are okay, but there is a fault at the end of this bus 9. So the current which will flow will be the voltage at this bus, which is 1 pu divided by the total impedance up to this point, and this will come something like this. I am not going in detail about these calculations because our main objective is to understand what are the effect and why we are going to consider these different types of topology for fault current calculations. So now suppose in earlier slides, if you see here, these generators at both the buses were in service. Now in this particular slide, generator at this bus is not in service. Only one generator connected at bus 1 is in service, and remaining whole system are in service. And now suppose there is a fault on this bus 9. In that case, my total fault current will be something like this. So what are these? What is the implication of this on our power system network? So if you see, because of the change in the network, because of the change in, suppose one bus in the system, suppose one line is out of service, or suppose one generator is out of service, my fault current is keep on changing. So we have to design a power system protection relays in such a way that it should take care of every types of possibilities. Like a protection system must be designed in such a way that it should take care when there is, suppose two generators are in service, it should isolate the faults. Even if one generators are in service, it should isolate the faults. Even if the fault is at the end of the bus or end of the network, it should isolate the fault. So in different types of systems, in different types of conditions, we have to design our system. And for the purpose of this designing, the next 2 or 3 important parameters are there. So what are these important parameters? First of all is sensitivity. So what is basically the sensitivity? Sensitivity means a relay shall be sensitive to operate for minimum quantity of operating parameters. So now if you see these earlier slides, what are the minimum operating quantities? It is 0.22 in this case, 0.229, and then 10 or 20. So even if I am designing a system with large number of networks, my protection system must be such that it should isolate the fault with minimum fault current. But at the same time, the system must be so secure that it should not operate for load current. Suppose in some cases, my load current is 100 ampere and minimum fault current is 110 ampere. So the system should properly discriminate between 100 ampere and 110 ampere. And this is the sensitivity of the protection system. Next, the selectivity. Selectivity means the relay should be able to select only the faulty section and it should isolate only the faulty section. So under no circumstance, my relay should isolate the non-faulted section. So this is selectivity. I am going to give the detailed description of selectivity in the upcoming slides. Speed, I have already explained in the initial third or fourth slide that the relay should operate as fast as possible to isolate the fault. Why it should operate as fast as possible? Because if you isolate the fault with minimum time, then the damage in the system will be minimum, because the time is minimum, so I square RT will be minimum. Stability, relay should be stable. It should not operate for undesired or the abnormal conditions which are not fault, suppose the overloading or the power swing. The relay should not operate during those conditions. It should remain stable. Reliability. Now, reliability is a very important concept. It is a mixture of two different concepts. One is your relay should operate only in when it is desired to operate. That means the relay should operate only for those faults in which it has to isolate the fault. At the same time, relay should not operate for the faults which are outside the operating zones of this relay. So there are two terms. One is dependable, that is whenever there is a fault in the system, my relay should operate. And another is secure. The relay should operate only for the faults which is inside its zone. And I am going to cover about the zones in the upcoming slides. So now this I have explained in the last slide itself. Reliability. Reliability has two different concepts. One, they may fail to operate when they are expected to. So relay should not fail to operate when they are expected to operate. It is another case, it might happen that the relay may operate when they are not expected to. So it should also not happen. So these two concepts will combine together, it will becomes the reliability. So now I will consider one example. This is a simple power system network, and we are having these three buses along with breakers B1, B2 connected between these two buses, B3, B4, B5 connected between these two buses, and these are the relays. Now suppose there is a fault at this point F. What should happen? Whenever there is a fault at this point, only my breaker B1 and B2 should operate. If the breaker B1 and B2 operates or opens and isolates the fault, then it is called the normal operation. But now suppose due to any reason the breaker B2 fails to open. Now this is a condition which is not desirable, and this condition falls under the category of dependability, because I want my relay to operate for this particular fault, but the relay fails to operate or the breaker fails to open, and this is the loss of dependability. Now, what is loss of security? Again, suppose there is a fault at this point, and now the relay R1 and R2 should operate, and it should open the breaker B1 and B2. But due to some reason, your breaker B5 also operates. Now, it is not desirable because we want only these two breakers should operate. So when this breaker B5 operates, due to any fault at this point F, so what happens now? There is a large scale disturbances. This line will be isolated and this line will also be isolated, and this is not desirable, because even if these two breaker opens, your fault will be isolated. So this is loss of security. So the two concepts, loss of security and loss of dependability, or the security and dependability combined together forms the reliability. Now what is selectivity? Selectivity means suppose there is a fault at this point F. Now for this fault at F, my relay R2 should operate, and if your R2 fails to operate, then R1 should operate. Again, for the selectivity purpose, your R2 should operate first. If R2 operates, there will be the minimum disruption in the power system network. Only R2, only this line will be isolated, and the second line will be in service. But now the next concept, which is your the backup. So suppose this R2 fails to operate, then your R1 should operate. And in this way, we can have multiple levels. Like suppose first level, the primary relays at this location fails to operate, then the next relay should operate. If this fails to operate, then the next relay should operate. and this is called the backup protections. So the primary protections are always desired to operate with minimum possible time, and then comes the backup protections which operates after certain time delays, and this operate only in case your primary protection fails to operate. We will discuss about this in details in the coming slides. This is primary and backup. I have already explained. Now the zones of protection system. What are zones of protection? If you see in the very first slide, I have explained that we have some synchronous generators followed by generating transformer, transmission lines, then some lower distribution or sub transmission level lines, then distribution, and at the end uh, we will have some loads. So we can have multiple zones like this. Generator zones, then the zone between the generator bus and the generator transformer, then the transmission lines, then distribution lines, like that. So we can have multiple zones. The primary requirement is that all the elements must be protected by its primary protection. All the elements must be protected for any fault in its zone. Whenever a fault is outside its zone, that relay should not operate, and it should operate only if the primary relay of that particular zone fails to operate. We will see in this slide. So this is synchronous generators, generator transformer bus. Then we are having large number of transmission and distribution lines. So these blue rectangles, if you see, these are for bus bar zones. So these are for the bus bar zones. Then we can have the zones for the transformers. We can have the zone for the synchronous generators. We can have the zone for the loads or the distribution lines. So in that way, we can create a large number of zones. And the prime requirement is that for any faults in one particular zone, it should the protection system should isolate the fault with minimum possible time, and only that particular faulted zone should be isolated. So now one of the most important concepts, from where this zone is defined, from where you can say that this is a zone of transformer, or this is a zone of transmission line, or this is a zone of bus bar. Basically, if we see, suppose this is a bus bar. In an ideal situation, what should have? We should have two CTs on either side of circuit breaker. If we have two CTs on either side of circuit breaker, then it is very easy to define a protection zones, because all the zones in a power system networks are always drawn from CT start points. So now if you have two CTs on both sides of breakers, then we can have one zone for the transmission line right from this circuit, this current transformer up to your transmission lines. Suppose from this is your feeder or transmission line. So this will be one zone. And from this current transformer, this will be the bus bar protection zone. And if you have two CTs on either side of circuit breaker, this is a very safest types of zone formation, because there will be no dead zones, there will be no end zone. Because suppose there is any fault between this circuit breaker or current transformer, this will be immediately cleared by your bus bar protection as well as feeder protection, because any fault between this current transformer and your breaker, it will be inside the bus bar zone. Also, it will be inside the feeder zone. If a fault is at this side of current transformer, that means that fault will be covered by the bus bar protection and it will be immediately isolated. If a fault is at this location, that fault will be immediately cleared by your bus bar protection as well as your feeder protection. If a fault is on the feeder side, then that fault will be immediately protected by your feeder protection. But generally, we don't have the two CTs on either side of breaker always. Most of the time, we have CT or only at one side of the circuit breaker. It can have this current transformer on the bus bar side, or we can have the current transformer on the feeder side. Even if we have a current transformer on the feeder side, what we generally do, we use two separate code, one for your bus bar protection and one for your feeder protection. And the start point is formed in such a way that now this from this CT to your up to this side, it will be covered by feeder protection, and this side will be covered by bus bar protection. Generally, these two are the same CT, because this is the same core, different cores of the same CT. Now, the problem with this type of system, which is very prevalent in our network, because generally all the network we are having this bus followed by the bus isolators, then circuit breakers, then your second isolators, and in between there is one CT. So now the problem is, if there is a fault between this current transformer and CT, if you see, if there is a fault between this current transformer and CT, this breaker will operate. Why this breaker will operate? Because a fault in between this breaker and CT at this location, it will be seen by this bus bar protection, and bus bar protection will operate and it will trip this bus bar immediately. But if you see now, even if your bus bar is tripped or even if bus bar is open, we will be having the fault continued or continuously feed from the feeder end, because the fault is here and the feeder is in the charged condition, and feeder cannot see this fault because this fault is on the opposite side of the start point of CT. So this fault is in the reverse direction. So either this feeder protection will see the fault, but it will see the fault in the reverse direction, which is the time delayed protection, maybe 500 or 350 milliseconds, depending upon the practice of different utilities. So now the feeder protection will see the fault in reverse direction and it will not operate. So what happens will our fault will keep on persisting in the system. Not to isolate those types of fault, we need another things, and we need some other types of protection that we will discuss separately if the time permits. Those types of faults or those types of system are generally called the end fault protection. You may have thought that suppose this CT is installed on the other side of breaker, that is the CT is installed on the bus bar side. Even if the CT is installed on the bus bar side, again there is a problem, because if the CT is at this side, suppose you have a CT on this side only and you don't have this CT. Now for any fault between the CT and breaker, this fault will be immediately cleared by your feeder protection. But even if your circuit breaker is opened by the feeder protection, fault cannot be isolated because it will be continued to be fed from bus bar. So you need the operation of bus bar, and this bus bar protection, if you have not implemented end fault protection, then this bus bar protection will operate through the LBB or breaker failure protection, and that will be time delayed. So this is one of the most important concepts for the zone of protection. I think this is this must be clear to all of you, how we define the zones, how the CTs are connected, what are the limitations of the CT on only one side. Now, one question might come that if there is a limitation of these types of delayed protection by having the CT on one side, then why don't we go for the two CTs on either side of breaker? Generally, if you go with these two CT on either side of the circuit breaker, then this will be a costly affair. So at the end, the everything will be compromised with the reliability, security, and at the same time the cost, because it is assumed that the chances of the fault between the CT and the circuit breaker are very less and very rare. So unnecessarily we are not going to use two CTs, and we are not going to increase the cost of the protection system. So now the zones. So if you remember this slide, uh, this slide wherein I have mentioned the different zones, that is the synchronous generators, generating transformer, transmission line, distribution lines, etc. So now if you see here in this, once you understand the concept of zone formation through current transformer, you can see that you will be having one zone for bus bar, and if there is any fault in this bus bar zones, then only the breakers connected to the bus bar should operate and all other systems should remain in service. This is the bus bar protection zone. Similarly, for transmission line protection zone, if there is a fault between any 2 points in this transmission line, then only these two breakers should operate and these should isolate the fault. All other remaining systems should remain in service. If you draw the zones for transformer protection, then it will include the breakers from the both side of the transformer, that is from the HV to the LV side or HV to the IV side, whatever you may say. So if there is a fault on the transformer, both side circuit breakers should operate and it should clear the fault as quickly as possible. If you have a fault on the distribution line, then only the breakers connected to the distribution line should operate. Likewise, if there is a fault on the motors, then only the breaker controlling that motor should operate. So this is the basic concept related to the zones, the basic concept related to the formation of the zones. Now we move to the standard device numbers. I am moving a little bit quickly, and if you have any doubt, you can always ask at the end. And if you think that I am moving very quickly or I am speaking very fast, then also you can say so that I can control. If it is okay till this point.
Sir, kindly continue. We will take all the question at the end of the session.
Okay, so now these are some of the standard device numbers. As per IEEE C37.2, I am not going to discuss all the different types of device numbers, because anyway that we can always search through Google. The device number which I am going to consider in this particular slide is only those device numbers which are important for our fundamental concept, like the circuit breaker 52, isolators which is 89, not mentioned here, then the time over current relay, that is 51, instantaneous over current relay 50, then the distance protection 21, 81 is carrier added protection, and master trip relay which is 86. We can have the different device numbers. No need to remember the device numbers, because whenever this is required, you can always search this on Google and use as per the convenience. Now, what are the different types of protection systems used in a substation? So in a substation, we can have transmission lines, transformers, reactors, and bus bar. And as we have already discussed earlier, we have the zones for different systems. So we can have the protection system for each zone. For the transmission line, we can have the distance protection or differential protection. Then we have some ancillary protection functions like SOTF, stub, DEF, over voltage, power swing, fuse failure, and broken conductor. I will discuss about each of these in the upcoming slides. Then the auto reclosure functions, which is generally a part of distance protection itself. Then for the transformer and reactor, we will be having two different types of protection functions. One is the mechanical, and the second is the electrical protection. In the electrical, we will be having differential or REF protections, and then for the backup and for the time delayed protections, we are having directional overcurrent and earth fault protections. And nowadays, we are using backup impedance protection also. For the mechanical protection, we are having buck holes, PRD, OTI, WTI, etc. The bus bar protection, generally for the bus bar protection, we use differential protection. And earlier days, we were using the high impedance differential protection. Nowadays, we are going towards this low impedance bus bar differential protection. In that low impedance bus bar protection also, we are having two different options. We can go for centralized or decentralized, and I will discuss about this in the upcoming slides. At the end, we are having local backup breaker protections or LBB protection. So now, what are the basics of transmission line protection? If you recall from the very first or second slide, wherein I have stated that if there is a short circuit on the transmission line, then what happens is that you are having an increase in current, at the same time a reduction in voltage. Based upon these two factors, that is current and voltage, we can design a protection system which takes these two quantities, voltage and current, and now it will calculate this ratio and it will give impedance, and it will continuously monitor this impedance, and whenever that impedance falls below a set limit, it will issue a trip command. So this type of system is called distance protection system. Generally, we have three different zones in forward direction, that is zone 1, zone 2, zone 3, and one zone in the reverse direction. Generally, zone 1 itself should cover the 100% of the protective line, but due to the limitations of your CT, CVT accuracies, relay accuracies, as well as the line parameters, we doesn't go for the 100% settings of zone 1. We generally set zone 1 at 80 to 85%, and then the remaining 15 to 20% is covered by zone 2. If you see here, this is zone 1, which is the 80 to 85% of the principal transmission line. Then we will be having a separate zone, which is zone 2. This is generally set as 120 to 150% of the principal transmission line AB. And generally, why we set 120? If you see here, this is 80. And this 80 we have achieved because of the four different parameters which can have some error on your protection systems, like the error due to current transformer, error due to voltage transformer, error due to your line impedance parameters like zero sequence and positive sequence parameters, error due to the relay processors or relay inaccuracies. So now if you consider all these factors at 5%, so the 4 errors will contribute to a maximum of 20%, either in the plus or in the minus direction. So if we select it at 80%, so even if all the errors are in the plus 5 directions, I will reach only up to this bus and I cannot cross this bus, and that will ensure only the outage of the principal transmission line. Likewise, the zone 2 is considered the maximum of 120%. I will discuss about 150% case also, but generally 120%. Why 120%? Because suppose now all the errors are in the minus 5 direction also. In that case also, that minus 5 minus 5 minus 5 minus 5, that is minus 20, it will reduce only up to this second bus or the remote bus, and my entire transmission line will be protected by this zone 1 and zone 2. Again, there is one limitation, because if you see this zone 2, it is encroaching, or it is in the zone 1 of the adjacent line from the remote bus. So your zone 2 must be time delayed. We need one additional zone, that is called zone 3. Zone 3 will be basically the backup of this remote bus. So if there is any fault on the remote bus, it should be isolated through the protection available at this bus. And if the protection at this bus fails to operate, then the protection at this bus should isolate the fault. And for that, one additional zone, that is zone 3, is used, which is basically your complete ZAB plus ZBC. And if you see again, this is 120%. Why 120? Because of those 4 factors in the plus minus 5%. If you select it at 120, so even if all those errors are in the minus direction, we will reach up to the remote bus from the remote substation, and the entire transmission line will be protected, as well as we will have the backup for the remote longest line from the remote bus also. These are some of the standard settings which is presently being used in Power Grid or in some different utilities also. Zone 1 is generally forward with 80% and instantaneous. This is for general conditions. If my line is having series compensation, in that case, this setting will change. But for general conditions, it will be 80%. Zone 2, 120 to 150% with a time delay of 0.35 to 0.5 second. Zone 3, it will be 120% of self line plus longest line at remote bus. Zone 4 or Zone 5, Zone 5 is in the ABB relay, Zone 4 in all other relay. It will be a reverse zone with 10 to 20% resetting and a time delay of 500 millisecond. Now, auto reclosing scheme. I am not going to discuss about the complete protection of transmission line, because this is a fundamental session only, and because of the time limitations, we will cover the important concepts. We will cover the fundamental concepts only, and if required some additional doubt, we will take after the conclusion of this session. So auto reclosure, generally it is used for in India, in most of the utilities, it is used for single phase faults. And in the single phase fault, it is assumption that most of these faults on the transmission lines, which are single line to ground faults, are generally transient in nature. And if you only open one pole of the circuit breaker, and if you provide a sufficient time delay for the deionization of the arc, and then if you reclose the breaker, then generally the line will hold and line will be energized. So the outage will be minimum, only about 1 second or 800 millisecond, or that too for only one particular phase. So this is the time delay of 800 or 1000 millisecond is called dead time. Then there is some second timer, which is the reclaim time. Reclaim time is basically used. This time is basically provided so that suppose there is a fault on the network, and first my auto reclosure relay operates and it closes the circuit breaker. Now there is a second fault immediately after the first fault. So what happens? There is a stress on your circuit breakers mechanism, because suppose this is a pneumatic breaker or this is a spring breaker. So once a circuit breaker opens and close, so after that open close operation, it requires some time for the air pressure buildup as well as for spring charging if it is your spring charge breakers. Also, if there is a fault between these two times, or if there is a fault uh, within a very short duration, suppose within 2 or 3 seconds, within 4 or 5 seconds, then it might happen that my circuit breaker mechanism is not ready to operate correctly, and it might fail during actual fault on the transmission line. So that's why sufficient time delay, generally at present a 25 second is provided, and it is assumed that within that 25 second the breaker mechanism will be ready for next operation. So the dead time generally 1 second, reclaim time 25 seconds. We are using priority AR in case of 1.5 CB scheme. And what is this priority AR? The priority AR is basically if there is a fault on your 1.5 breaker scheme transmission line having 1.5 breaker scheme, then both main and tie circuit breaker will open first. Then after a time delay of 1 second, only main breaker will close, and then after a further time delay of 1 second, your tie breaker should close. So if there is a fault, permanent fault on the transmission line, you will save one operation of the tie circuit breaker. These are some of the conditions in which we block the auto reclosure, like for the bus bar protections, LVB protection, over voltage, zone 2, zone 3, and circuit breaker problems, etc. Now, the transformer and reactor protections. Like I have already explained in the earlier slide, for the transformer reactor, we are having the differential, REF, backup impedance, T differential for bus reactor, then the overfluxing, backup overcurrent at fault protections for HV and IV side. Presently, we are also using backup impedance protection. So now, how this differential protection works? Basically, you can have two different types of differential protection. It can be the high impedance type, or it can be the low impedance type. But for suppose this is a low impedance type, so what I have done is I have connected the HV side CT or IV side CT or LV side, whatever it may be, the HV and LV side CT to your relays, and now the relay will calculate the differential and stabilization current based upon the current magnitude from the HV and LV side, and simple Kirchhoff's law will follow. So in normal condition, whatever current is entering into the zone, same current should take out, and it will be balanced. In case there is a fault inside the zone, so the current entering and current leaving will not be equal, and the differential protection will detect the fault. So for transformer, what we need is we need a triple pole feature. That means whenever there is a fault on transformer, we want our relay to operate, and it should trip the all three poles of both side of circuit, both side of the transformer breakers. Then it should be of multi-bias setting, and it should not operate during inrush. And this inrush is important for transformer case. Inrush is not that much important for reactor because of the designing issue. The designing of reactor is generally designed on the linear portion of your BH curve, while the transformer is designed on the knee, closer to the knee point of the BH curve. So there is a chances of higher inrush current in case of transformer. In case of reactor also, because we are using air gap core, so because of the higher reluctance of the magnetic path, the inrush current will be lower. Now, again, these are some of the factors which limits your differential protection of transformer. You can have the transformer magnetizing current, tap changing error, CT error, and if you combine all, we will be having these type of error continuously in the differential zone. So we have to select my differential protection in such a way that it should not operate for any fault in this. Means if there is a differential current because of this CT error or tap changing error or transformer magnetizing current, it should not operate. It should operate only for the actual fault on the transformer, and that's why we are having two slopes and one initial pickup. Now these are the mechanical protection, which is uh, very generic, and I am not going to discuss in details about this. Now for the restricted earth fault, if you see the transformer, this point, the minimum threshold for a differential protection, we generally set it at 10 to 20% of the transformer rated current. Now suppose there is a fault at the close to the neutral of the transformer. In that case, what happens if there is a fault closer to the neutral of the transformer? Then you may have a very a small amount of current, and that small amount of current might not operate the differential protection, and so we need an additional protection for protecting that region, and that's why we need a protection which protects that smaller region. And what now we are doing, we use three CTs of the phase side, one CT of the neutral side connected in parallel, and it will be connected to a relay which may be Generally, it is a high impedance type relay, and you will be having a stabilizing resistance followed by a metro cell in this path. And this relay will operate for all the faults which are closer to neutral. Uh, Definitely, it will operate for other faults also, but it will take care of those faults which are generally not cleared by differential protection for some or other regions. Now, bus bar protection. For bus bar protection, earlier days, the concept that were used was for the concept was the main zone and check zone. Basically, what happens? You are having n number of elements connected to the bus. The sum of all the currents entering to the bus must be equal to the sum of all the current leaving the bus. Now we use main zone, that is the zone for the bus 1, zone for the bus 2, and we use a zone of complete substation which will be independent of your isolators. And if this check zone and the main zone 1 detect the fault, then your bus bar 1 will operate. If the check zone and main zone 2 will detect the fault, then your bus bar uh, 2 will trip. So now in present days, we use the numerical low impedance bus bar relays, and generally these are of two types. One is your decentralized type and one is centralized type. This is the centralized type of relay in which there is one central unit and the current of all the particular feeders, all the break CT are coming up to this relay, and this relay will calculate the differential current and stabilization current. And if it sees that your differential current and stabilization current is as per your above these settings which we have set for the bus bar fault, then it will issue a trip command, and you can see that all the trip command will flow from this central unit to the breaker. So there will be large number of copper wires from this central wire to breakers as well as from the CT to the central unit. Now, in case of decentralized, the currents of the particular feeders or particular base are measured at that level only, or at that kiosk, if there is a kiosk or SPR, or in particular data acquisition unit. This is called bay unit. So for each feeder, you are having one data acquisition unit. Current will be measured here. Then this current will be transferred to the central unit. Central unit will calculate the differential and stabilization current. If it sees that it is a bus bar fault condition, it will inform all the data acquisition units. And now data acquisition unit will trip the circuit breaker. So your copper cable will be from this data acquisition unit to breakers and from the current transformer to data acquisition unit only. So there will be a huge reduction in copper cable, but at the same time, this has certain limitations. Like suppose this fiber optic cable becomes damaged. In that case, your bus bar protection will be in the block condition. Now the LVB protection is a very simple protection. If you see here, suppose there is a fault on this transmission line, what should happen? This breaker should trip. If this breaker fails to trip due to any reason, then all the other feeders or all the other breakers which are feeding this fault must be tripped. So at this present case, this B, D, E, and C, this must be tripped. This is called back trip. And since this fault might be also fed from the remote end, for that we have to send the enter trip. Now this is an example of 1.5 breaker scheme. So suppose there can be two different conditions. One is suppose there is a fault on this transmission line. Uh, Ideally, these two breakers should operate, but suppose due to any reason this breaker fails to open. Now what happens if this breaker fails to open? So to isolate this breaker, we have to isolate this bus. So we have to trip all the breakers connected to this bus. At the same time, we have to send a remote trip command to your line so that this point is in the de-energized condition. Uh, at the end, we are having some carrier aided protections also. So these carrier aided protections, you can have two different types. One is permissive underreaching and one is permissive overreaching. In the permissive underreaching schemes, zone 1 generally sends the carrier, and this permissive underreaching and permissive overreaching schemes, generally the carrier aided schemes are used for the protection of this 80 to 100% of the transmission lines which are between after the zone 1 boundary to the remote bus. So you can have two different types of scheme: permissive underreaching, wherein your zone 1 will send the carrier, and permissive overreaching, wherein my zone 2 will send the carrier. So if you see here, zone 1 at this end, this relay sees the fault in zone 1, it has sent the carrier. This carrier is received at this end, and if the zone 2 is in the pickup condition, it will issue the trip command. Likewise, for permissive overreaching, if there is a fault at this point, since this fault is in zone 1, so definitely this fault will always be in zone 2. So this relay will send the carrier, and once the carrier is received at here, and if zone 2 is in pickup condition, it will issue a trip command. Now, only some ancillary functions, and these are very basic functions like SOTF. What is SOTF? SOTF is basically switch on to fault. So whenever we are closing a circuit breaker onto existing fault on the transmission line, in that case your voltage might not develop properly and you are having a large amount of current. So you want this fault to be isolated as quickly as possible, and for that we use SOTF feature. Second is power swing. So whenever there is a sudden load change due to fault anywhere in the network, then we use the power swing concept, because in the power swing what happens, the impedance is keep on reducing very slowly, and slowly it will enter into the zone boundary. While in case of fault in the network, my zone impedance or the locus of the impedance will enter into the zone immediately. So the relay internal algorithm will detect this time which your impedance takes from the outside of the zone to uh, enter inside the zone. And if this is a very less time, it will detect it as power swing. And now we can have two different options. We can block all zones, or we can block all zones except zone 1. This depends upon different utilities. Generally in power grid, we are using block all zone features. A stub protection, it is basically used for 1.5 breaker scheme. Now in case of 1.5 breaker scheme, if you see, if your line isolator is open, the CVT voltage will not be available to the distance protection relay, and in that case your distance protection relay will not work properly. So now since your voltage is 0 and only current will be available, and in that case we have to enable one protection function which is which will operate only on the basis of your current threshold. That protection which operates only on the basis of current threshold and after the line isolated open status is called step protection, and applicable only for 1.5 breaker scheme. Fuse failure, it is again a very important thing, because if suppose the fuse of any one out of the 3 phase fails, so what happens? Now there is reduction in voltage, but there is a current present in the system, so your impedance might fall. And if this impedance might fall, and if the relay detects it as fault, it will issue a trip command. But actually this is not a fault condition, this is only a problem in the secondary circuit. So what happens, the relay will use a simple algorithm. It will see the conditions of your zero sequence and negative sequence current and zero sequence and negative sequence voltage. In case of fault, there will be a presence of zero sequence current and zero sequence voltage, while in case of only VT fuse fail, you will be having zero sequence voltage but not zero sequence current. So relay will immediately detect it as a fuse failure condition and it will block the distance protection. Likewise, the broken conductor, in that case, you will be having the presence of zero sequence current but no presence of zero sequence voltage, and the relay will issue alarm based on the settings. If you are using for alarm, it will issue an alarm. If you are using for trip, it can issue a trip command. Some relay uses the concept of I2 by I1, that is negative by positive sequence current ratio. Some relays like Siemens 7SA522, it uses the concept of the maximum to minimum phase current ratio. So that's all for this session, and that's it from my side. In case of any doubt, you may ask.
Pankaj ji, thank you very much. It was mind blowing, and I feel no one can give better presentation on the fundamentals of power protection that you have given. We are very thankful. You take a rest of 2-3 minutes. Before I invite any question, you can have glass of water, and I would like to invite PP Bhai Saab. Kindly unmute yourself and say a few words about Pankaj sir. Bhai Saab, please unmute yourself. Saket ji,
Rajesh, are you getting me?
yes, please, sir.
Hello. You are getting me, please?
Yes, sir. Please continue.
Yeah. It has been a wonderful presentation by Pankaj. I think exactly you have said it is a mind-blowing. No words with me as well to speak about his presentation. made a wonderful presentation. You see, I think he's really gem of a person. And the slides were really very lucidly made, I think, to make us understand the things very quickly. And I must say that I must have worked very hard before coming to make the presentation. So I hats off to him. Once again, I think he has touched all components of the basic protection, right? Starting from what is basic protection, what is protection for the transmission line, what is protection for transformers, reactors. Then he has touched zones in a very nice lucid way. How they overlap, how they help take care of the system in a very effective manner. And I again put it, then he has touched the other things, the auto close, and then the fuse relays, fuse system, every small thing, I think he has touched so beautifully. Hats off once again for him. And my special appreciation, Rajeshji, for you. You are always striving your best. I think in the past few months and couple of years, you have done a great service to the country. See, arranging all such sort of conferences, videos, and then you see started the dialogue. You see on the YouTube, and then so many other tips for all of us in the country. And no words with me. Finally, to say salute you, salute Pankaj for a wonderful evening. Thank you so much for that.
Sir, I have expressed in the beginning of my presentation that it couldn't have been possible without the support of people like you. And every time you are
no, sir, no.
BMW.
A very small person, but I say you, I never expected that you will put in so hard work. I was watching you for the last 10, 12 years, but Rajeshji, you have excelled all my imaginations and surpassed it. But I really salute you, no words, honestly, and no exaggeration from my side. Pankaj, you have done a very good job. Thank you so much, both of you.
Pankaj, now time to take question. Are you ready?
Thank you so much. Thank you.
Okay, and now the person can raise their hand and unmute one by one so that the Pankaj can answer all the queries you have in your mind. Sakeji, unmute one by one if there is some hand raises.
Sure, sir.
Dr. Kishan wants to ask something. Kindly allow him to speak.
First of all, thank you very much, sir, for this wonderful session. Actually, I have cleared so many of doubts with this presentation only. Pankaj sir, I have a particular question not belongs to this session actually. Actually, what we are finding that we have some fault current and fault rated. Actually, what I want to ask particularly, transformer have a rated MVA, and some substation companies are giving us fault current MVA. And when we are calculating the fault, I have a fault MVA of 8,000 MVA rating, and it is a substation of 132 by 6.6 kV. Primary is 132 kV line, and it is stepped down to 6.6 kV. When I'm calculating the fault current with simple formula, that is fault MVA divided by √3 into V phase to phase voltage, it is actually coming more than 600 kiloamps at low voltage side. Is it really feasible to design the earthing system or other protection systems with this level of fault current? Pankaj sir.
You have correctly calculated it is coming 600 kiloamperes.
Yes sir, yes sir.
I think
is it
really not possible? 600 kiloamperes so not possible. The fault generally the transformers or the equipments that are provided at our substations. So whenever we are using any transformer, suppose it is a 315 MVA 400 by 220 kV transformer, then the calculation for your fault current, there are two different things. One is the basic rated current that you generally you can calculate for 315 MVA and for 400 by 220 kV transformer. It will be 455 for HV side and 826 for LV side. And now the short circuit current, suppose there is a fault on the bus of our system, fault on the HV bus or fault on the LV bus. So generally when it is calculated through some software, through the fault calculation software. So it should be in the range of 40-50 kiloamperes, and it is generally limited in that way only, because if suppose your fault is 100 kiloamperes or 150 kiloamperes, then we cannot have a breaker for that rating. So if you have a fault calculation, if you have calculated and if it is correctly coming to 600 kiloampere, then there might have two possibilities. First, just check the calculation once again, make sure that it is exactly correct. Then we have to because we cannot design any earthing system or we cannot design a breaker to take care of that 600 kiloampere fault current. So you have to again calculate the different portions of the network, different components which are connected to your network. And I don't think that 600 kiloampere is possible. If it is possible, you can share with me and I will revert back to you. You can share with me on the email.
Exactly. Thank you. Actually, sir, I was also thinking the same, that what I have collected from the substation is not correct. So
I can add one thing. I can add one thing. Actually, what happens sometimes the substation people provide you the base MVA, short circuit MVA. That seems to be on the higher side, but actually there is some limits on for 400 kV system. 63 kiloampere the maximum limit. For 220 50 kiloampere, for 33 and 66 kV 31.5. Likewise, there are some limits are there. That can't be beyond that, because there are so many impedance are coming. The fault happens when the fault starts from the source up to the point of fault. So many impedance are coming in the series, and in no case can go up to 600 kiloampere in the present scenario.
Exactly, sir. Because it's coming beyond the lightning current itself, sir.
Right.
So the data was not correct.
It is a base MVA value, I think.
Okay. Thank you so much, and thank you, Pankaj sir, for this beautiful presentation. Actually,
now Ramdhani ji has raised hand. Kindly unmute Saket ji.
Yes, very good evening to all of you, sir. And thank you so much, sir, for a wonderful presentation and session. We have learned a lot of things, sir. And thank you, Pankaj, sir. You deliver a beautiful presentation. Really, we have learned a lot of things from you and your presentation.
Thank you.
Sir, मेरा एक ही क्वेश्चन है सर कि why relay known as a brain of the power system? Sir, can you elaborate in detail, sir?
देखिए, आपका जो मेन हमारा सिस्टम है, मेन सिस्टम में क्या है कि जैसे जनरेशन है और जनरेशन के बाद लास्ट पॉइंट पे लोड है, और इसके बीच में बहुत सारे एलिमेंट्स आ रहे हैं, मतलब ट्रांसमिशन लाइन, डिस्ट्रीब्यूशन, जो भी चीजें हैं। तो इसको आप एक पूरा बॉडी मान सकते हैं कि एक पूरा बॉडी हमारा एक पार्ट हो गया, एक पॉइंट से दूसरे पॉइंट तक। अब इस पूरे बॉडी में जब भी मतलब कहीं पर भी कुछ भी प्रॉब्लम आता है, जैसे हमारे जनरेशन से लेकर के और लोड के बीच में कहीं पर भी कुछ भी प्रॉब्लम आता है, तो सबसे पहले हमारी बॉडी में कुछ भी प्रॉब्लम आता है तो हमारी बॉडी का कौन सा पार्ट सबसे पहले उसे सेंस करता है, कौन सा पार्ट हमें बताता है कि भाई कुछ प्रॉब्लम आ रहा है? हमारे माइंड को मतलब जो है उसमें सबसे पहले हमें एक सिग्नल आता है कि कुछ मेरे को प्रॉब्लम हो रहा है, मेरे सपोज हाथ में दर्द हो रहा है, पैर में दर्द, कुछ भी हो रहा है, तो वो आता है। सेम वे अगर मेरा एक सिस्टम है जिसमें बहुत सारे एलिमेंट्स है, ट्रांसफार्मर, रिएक्टर्स, ब्रेकर्स, आइसोलेटर्स, रिलेज, तो एक ऐसा चीज जो कि आपको सबसे पहले सिस्टम की कंडीशन को बताता है, वो क्या है? जैसे हमारे बॉडी में आपको जो ब्लड है नीचे से ऊपर तक जब फ्लो कर रहा है और ब्लड माइंड में जा रहा है और वही आपको इन्फॉर्मेशन कैरी करके पहुंचा रहा है, सेम वे जो रिले है उसमें आपका इन्फॉर्मेशन फ्लो हो रहा है एक एंड से दूसरे एंड तक, करंट और वोल्टेज। अब जैसे ही करंट वोल्टेज में कुछ भी इसको चेंजेस नजर आ रहा है तो उसको एक सिग्नल मिल रहा है कि भाई कुछ तो प्रॉब्लम हुआ है, और ये कुछ तो प्रॉब्लम जो हुआ है इसके कारण से वो ब्रेन है जो कि उसको पता चल रहा है। अब वो सिर्फ ब्रेन है, वो आगे कुछ कर नहीं सकता है, उसको कंट्रोल नहीं कर सकता, क्योंकि वो, मैं बीमार हो ही सकता हूँ, मैं ऐसा नहीं कर सकता कि मैंने सोच लिया बीमार नहीं होऊंगा तो नहीं होऊंगा, लेकिन ब्रेन को पता चला कि बीमार है तो अब वो एक्शन ले सकता है। तो एक्शन लेने के लिए वो किसको बोलेगा? आपके ब्रेकर को। तो ब्रेन ब्रेक मतलब आपका रिलेज है, और बाकी जो भी प्रोटेक्टिव आपके एलिमेंट्स है जैसे ब्रेकर्स, तो ब्रेकर्स को ये बोलेगा कि भाई आपको ट्रिप होना है। और ब्रेन को जैसे सिग्नल मिलते हैं हमारे पास ब्लड और इन सबसे मतलब जो सेल्स है, ऐसे इनको सीटीपीटी से मिलते हैं। तो सेम आप एक एनालॉजी बोल सकते हैं कि एक मेन कंपोनेंट जो कि सिस्टम के हेल्थ को सबसे पहले आपको बताता है कि सिस्टम में कुछ एबनॉर्मेलिटी आई है, तो सबसे पहले उसी को एबनॉर्मेलिटी समझ में आएगा, तो इसलिए उसको ब्रेन बोला जाता है।
सर क्या इससे अर्थिंग सिस्टम से सर क्या लिंकअप है, अपना रिलेशन है कुछ रिले का?
कौन से सिस्टम से?
अर्थिंग सिस्टम से सर रिले का कुछ
हाँ,
कनेक्शन है अर्थिंग सिस्टम से?
बिल्कुल है। अर्थिंग से मतलब बहुत ज्यादा लिमिटेशन है। आप देखेंगे तो अर्थिंग जैसे जिस सेंस में मैं बात कर रहा हूँ, अर्थिंग दो डिफरेंट सेंस में हो सकता है। एक को हालांकि अर्थिंग को ग्राउंडिंग बोला जाता है, जहाँ पर कि जो हमारा सेकेंडरी टर्मिनल्स की ग्राउंडिंग है उसके बारे में बाद में आता हूँ। एक आपका जो अर्थिंग है, अर्थिंग का जो सबसे इंपॉर्टेंट है, आपके डिफरेंट डिफरेंट टाइप्स के सिस्टम हो सकते हैं। जैसे मान लीजिए आइसोलेटेड है, या फिर सॉलिड ग्राउंडेड है, या फिर पीटरसन कॉइल्ड है। आपके जो डिफरेंट टाइप्स के अर्थिंग है उसके कारण से जो हमारे फ्लो ऑफ जीरो सीक्वेंस करेंट्स होते हैं वो उसके थ्रू ही लिमिट्स होते हैं। और जितने भी हमारे प्रोटेक्शन होते हैं, जैसे कि आपका मान लीजिए सिंगल लाइन टू ग्राउंड फॉल्ट है, मतलब जिस भी फॉल्ट में ग्राउंड इन्वॉल्व है, तो ग्राउंड इन्वॉल्व होगा तो आपका जीरो सीक्वेंस कंपोनेंट्स करंट का आएगा। और उसके बेसिस पर जो हम जितना भी मतलब प्रोटेक्शन सिस्टम डिजाइन कर रहे हैं, उसमें दो ही मेन चीज रखा जाता है, जीरो सीक्वेंस और नेगेटिव सीक्वेंस। और फिर आपका एक तो कि किस पॉइंट पर हमारा जो सिस्टम का अर्थिंग है वो कहाँ पर है। जैसे कि अगर मान लीजिए एक मैं छोटा एग्जांपल लेता हूँ, ट्रांसमिशन लाइन में सिंगल लाइन टू ग्राउंड फॉल्ट हुआ। अब इसका जो पाथ बनेगा, उसका पाथ क्या बनेगा? अगर सिंगल लाइन टू ग्राउंड फॉल्ट है, सपोज मान लीजिए कि मेरे टावर पे कुछ फ्लैश ओवर हुआ, तो वो एक आर्क है उसका जो फॉल्ट का, फिर फाइनली जो मेरा ये टावर का फुटिंग रेजिस्टेंस है वो, और अगर आपके ऊपर लाइटिंग के लिए बहुत सारे मतलब मैं जो अर्थ वायर वो लगा रहा हूँ, तो एक पैरेलल पाथ बनता है। अब अगर ये जो आपका अर्थ जो हम यूज कर रहे हैं वो कितना एक्यूरेट है, कितना स्ट्रॉन्ग है, इसके हिसाब से जब हम आज तो बहुत ज्यादा डिटेल में हम गए नहीं है, डिस्टेंस प्रोटेक्शन की जब बात करते हैं तो हम लोग सभी चीज अभी रिएक्टेंस के टर्म में बात कर रहे हैं। जब हम रेजिस्टेंस के फॉर्म में जाते हैं तब बहुत ज्यादा फर्क पड़ता है। अगर आप डिस्टेंस प्रोटेक्शन को थोड़ा सा डिटेल में पढ़ेंगे तो आपको समझ में आएगा कि हम कैरेक्टरिस्टिक में कैसे मूव कर रहे थे, कि प्लेन इंपिडेंस और फिर क्वाड्रिलेटरल मोवो, और आज की डेट में जो मतलब पॉलीगन या टोमेटो कैरेक्टरिस्टिक है वो कैसे आया। तो ये अलग अलग, क्योंकि जिस टाइप का अर्थिंग होगा उसके बेस पे आपका वो करंट डिटरमिन होगा, और जैसे करंट के हिसाब से आपका सिस्टम में जो भी चेंजेज आ रहा है उसी को फिर हमें इम्पिडेंस या फिर बोले मतलब रॉ टर्म में कि जो फॉल्ट रेजिस्टेंस है उसे इंक्लूड करना है हमारे नेटवर्क में।
ओके सर, थैंक यू सो मच सर, वंडरफुल एक्सप्लेनेशन।
वेलकम।
Next question, please. Umesh ji, kindly ask your question.
Hello. Are you getting?
हाँ, यस
Sir, please continue.
First of all, I would like to thank for such a wonderful presentation where you have covered, I think, all the aspects of the protection system in such a short span of time. For young engineers, it is really, I think, I would like to say that they should study further from here. You have touched all the principles, all the aspects, and even all the elements of the power network where the different kind of protections are used. Uh, my question is basically related to distribution network, sub-transmission network in Delhi. We are having 33 kV and 66 kV feeders. And these feeders are mixed type of feeders, I would say. Somewhere these feeders are underground, somewhere overhead. So what is your say for these feeders? Would you like to recommend the auto reclosure schemes for to be commissioned on such feeders or not?
सर फर्स्ट ऑफ ऑल थैंक यू। और सर ये है कि देखिए सर हिंदी में बोल सकते हो ना?
हाँ, नो इश्यूज, नो इश्यूज।
ठीक सर सबसे पहले तो ये है कि जनरली जो ये मान के चलते हैं कि हम कि केबल में परमानेंट नेचर के फॉल्ट होते हैं तो जनरली ऑटो रिक्लोजर अवॉइड करते हैं कि ऑटो रिक्लोजर नहीं यूज करना, ट्रांसमिशन लाइन में ही करते हैं, मतलब ओवरहेड ट्रांसमिशन लाइन में करते हैं, केबल्स में नहीं करते हैं। बट आज की डेट में सर आप देखेंगे तो जीई और एससीएल ने एक नए टाइप का सॉल्यूशन वो लेकर के आए हैं मार्केट में। उसमें क्या है कि आपका अगर केबल वाला भी सिस्टम है जिसमें कि मतलब हाइब्रिड है, आधा केबल है और आधा हमारे पास ओवरहेड ट्रांसमिशन लाइन है, तो वहां पर हम ऑटो रिक्लोजर को यूज कर सकते हैं। तो सिंपल क्या करता है कि एक न्यू सिस्टम आया है अभी मार्केट में, रिसेंटली आया है सेल और जीई का, जिसमें कि जहां से अपना ओवरहेड खत्म होकर के और केबल पोर्शन शुरू हो रहा है, वहां पर वो एक डिवाइस लगाता है ट्रांसमीटर रिसीवर टाइप। और अगर मान लीजिए कि हमारा फॉल्ट ओवरहेड लाइन सेक्शन में है तो आपको वो ऑटो रिक्लोजर के लिए इनेबल करेगा, और अगर फॉल्ट केबल वाले पोर्शन में है तो ऑटोमेटिकली आप वो ब्लॉक कर देता है ऑटो रिक्लोजर को। जनरली क्योंकि अगर हम पूरा कुछ भी ना लगाएं और ये मान के चले कि ऑटो रिक्लोजर यूज करना है, तो यही एक ही प्रॉब्लम रहता है कि हम ये मान के चलते हैं कि केबल्स के जो फॉल्ट है वो परमानेंट नेचर का है और उस पर अगर हम और क्लोज कर रहे हैं तो हम अननेसेसरली सेकंड स्ट्रेसेस डेवलप कर रहे हैं, तो इसलिए नहीं करते हैं। पर अगर हम इस टाइप का कोई सोल्यूशन यूज करें तो कर सकते हैं। अभी पावर ग्रिड में एक दो जगह पे मतलब ट्राई कर रहे हैं, अभी तो यूज नहीं किया है, लेकिन वो ट्राई कर रहे हैं इस सॉल्यूशन को जहां पर कि हाइब्रिड टाइप की लाइंस है और उसमें ऑटो रिक्लोजर के लिए जा रहे हैं।
तो इसमें एक चीज समझ में आती है पंकज जी, कि
हम्म।
बेसिकली आपको ये इंफॉर्मेशन डेफिनेट होनी चाहिए कि कहाँ पर अंडरग्राउंड है, देन ओनली देन अकॉर्डिंग टू द इंफॉर्मेशन यू fetch from the network, and accordingly it may be means reconciled with the protection system, and then we may use it. But
यस सर।
where we are having multiple overhead and underground portions of the network, I think your say is that it should not be commissioned. But on the other side, you see, even on the overhead networks, where I would like to say that complete line is even overhead, but it is accessible to the residences or houses, buildings, etc. Like in big cities like Delhi, Delhi में है, अगर accessibility है और कोई उसके means if there is a some fault and we reclose it, then there are chances that कोई अगर electrocute हो रहा हो, कुछ हो रहा हो, तो वो प्रॉब्लम एग्रेवेट हो जाए। तो उस केस में क्या कहेंगे आपके, ये हमें करना चाहिए कि नहीं इस तरह के सिनेरियोस में?
सर देखिए ये जितने भी मतलब इस टाइप के जो ये सिचुएशंस है वो केस टू केस डिपेंडेंट है। अब मान लीजिए कि जो अपने जनरल प्रैक्टिस में तो ऑटो रिक्लोजर हम ओवरहेड में यूज कर रहे हैं, लेकिन अगर हमारा ऐसा है जहाँ पर कि हमें लग रहा है कि बिल्कुल रेसिडेंशियल एरिया से ही क्रॉस हो रहा है और कुछ चांसेस है कि एक्सीडेंट हो सकता है, इलेक्ट्रोक्यूशन हो रहा है, और हम दो चीजें हैं सर, एक तो ये वाला पोर्शन तो है कि जहाँ पर कोई इलेक्ट्रोक्यूट हो रहा है, अगर हम ऑटो क्लोज करेंगे तो आपका उसको तो मतलब वो तो डैमेज होगा ही। लेकिन दूसरा होता है कि हमारे खुद का जो यूटिलिटी का अपना डिसीजन, जैसे मान लीजिए कि क्या हम किसी लाइन में अगर सिंगल लाइन टू ग्राउंड फॉल्ट है तो हम उसे परमानेंट आउट कर सकते हैं, मतलब हमारे पास इतना सिस्टम में मार्जिन है कि कोई एक लाइन जैसे दिल्ली वगैरह साइड में जितना एग्जैक्ट तो आपको पता है, जितना मुझे लगता है कि मान लीजिए कि कोई एक लाइन क्रिटिकल लाइन हम आउट कर रहे हैं तो ऐसा तो नहीं है कि बाकी लाइनें स्ट्रेस हो जाए और वो हमारे आउटेज के कंडीशंस पर आ जाए। तो ये दोनों के बीच का एक ट्रेड ऑफ है कि अगर हमें लगता है कि पर्टिकुलर एरिया से जा रहा है जहां पर कि मतलब फॉल्ट जो भी आएंगे मतलब ट्रीज वाले फॉल्ट नहीं है, ट्रांजिएंट नेचर की फॉल्ट नहीं है, परमानेंट फॉल्ट है, और मुझे वहां पर ऑटो क्लोज करने से प्रॉब्लम है, तो मैं ऑटो क्लोज को अवॉइड कर सकता हूँ। लेकिन साथ ही साथ फिर ये देखना पड़ेगा कि अगर मैं वो लाइन को आउट रखता हूँ तो क्या मेरा बाकी जो पूरा नेटवर्क में जो पावर रिक्वायरमेंट है वो मीट हो रहा है या नहीं हो रहा है। अगर ये दोनों कंडीशन सेटिस्फाइड हो रहा है सर तो फिर कर सकते हैं, क्योंकि एक
नहीं, एक सवाल और है बस डॉक्टर राजेश से। राजेश जी, कई बार जो है आपने देखा होगा इवन इलेक्ट्रोक्यूशन हो जाते हैं 33 kV या 11 kV की सर्किट से, तो लोग फील्ड में इवन समटाइम्स आई हैव सीन फ्रॉम इलेक्ट्रिकल इंस्पेक्टर के तरफ से भी वो ना डेटा मांगते हैं, रिले का फॉल्ट रिकॉर्ड और ट्रिपिंग मांगते हैं। क्या आपको लगता है कि ये रिलेवेंट है इन केस ऑफ इलेक्ट्रोक्यूशन?
Actually, what happens, the most of time the electrocution happens because of known operations of relay intended for that function. Actually, what happens when a electrocution is like a single phase to ground fault. The fault starts flowing, but that is a high impedance fault. The current is not as high as you find in the single line to ground fault. But there should be some provisions that should take care of that kind of current also. And if the data are demanded by that inspectorate office, they just want to do some R&D and they want to collect data. What kind of faults are happening in the distribution sector? What are the main causes? That is the only reason I think.
नहीं, लेकिन अगर मान लीजिए अगर डेटा देने के लिए है ही नहीं उस समय पर, मान लीजिए कोई इवेंट ऐसी हुई है जहां पर के इलेक्ट्रोक्यूशन हुआ है बट रिले सेंस ही नहीं कर पाया उसकी,
Sir, actually now the scenario has totally changed. With the coming of the private distribution company, they have come out with a very new technology kind of relay even at the 11 kV system that you are also using in your system, and that numerical relays may have all the data of current, fault current that flowed at that particular time, and that data can be given. Yes, when you are using the electromechanical relay, that is not possible, I do agree, but we have to work in the direction where we can utilize the technology we have.
थैंक यू।
Okay. Vikulji, last question. We are going to take the last question. Kindly unmute and ask.
सर नमस्कार। पंकज सर नमस्कार सर।
नमस्कार।
मेरा एक क्वेश्चन था कि ट्रांसमिशन लाइन में जो कॉपर बॉन्ड या एडिशनल अर्थिंग या अगर प्रॉपर अर्थिंग टावर की नहीं है तो डिस्टेंस प्रोटेक्शन की एक्यूरेसी पे क्या फर्क पड़ेगा सर?
अगर आपका प्रॉपर अर्थिंग नहीं है तो बहुत ज्यादा फर्क पड़ता है। सिंपल सा है, आप मान लीजिए कि टोटल जो डिस्टेंस प्रोटेक्शन है वो क्या है, इम्पीडेंस है। इम्पीडेंस क्या है, एक्स और आर है। जिस पॉइंट पर फॉल्ट आया आपका एक्स तो फिक्स है, मान लीजिए 10 ओम रिएक्टेंस है, 10 ओम तो फिक्स है। रेजिस्टेंस हम मान के चलते हैं, अगर आइडियल कंडीशन होता तो आप आर का रेजिस्टेंस मान लीजिए कि 1-2 ओम कुछ भी है और टावर फुटिंग का मान लीजिए कि 5-6 ओम है, तो हमारा टोटल रेजिस्टेंस आना चाहिए था 6 ओम। तो आपका 6 ओम रेजिस्टेंस है और 10 ओम रिएक्टेंस है, इसके हिसाब से कुछ इंपीडेंस आएगा। अब अगर प्रॉपर अर्थिंग नहीं है तो क्या होगा कि उस पॉइंट का आपका रेजिस्टेंस बढ़ा, तो वो वाला रेजिस्टेंस, जैसे आपका रेजिस्टेंस का मैग्नीट्यूड बढ़ गया तो आपका ये टोटल इंपीडेंस है वो बढ़ जाएगा। तो आपका मान लीजिए कि पहले इंपीडेंस आ रहा था 10 ओम, अभी इंपीडेंस कुछ रेजिस्टेंस के चेंज होने के कारण से इंपीडेंस आ गया 20, और जो हमारा जोन 1 है सपोज कर लेते हैं कि 15 पे सेट है, तो एक्चुअल फॉल्ट जोन 1 का है, पर रिले उस फॉल्ट को जोन 1 में देखेगी ही नहीं। रिले को ऐसा लगेगा कि फॉल्ट जोन 2 में है और रिले हमारी ऑपरेट नहीं करेगी या डिलेड ऑपरेट करेगी। तो सिंपल ज़्यादा सबसे सिंपल चीज़ है कि आपको पूरा जो ये है ना फॉल्ट, उसको रेजिस्टेंस और रिएक्टेंस के टर्म को कंबाइन करके वैसे इंपीडेंस में समझेंगे तो बहुत इजीली समझ में आ जाएगा कि अगर आपने रेजिस्टेंस बढ़ा।
Apart from that, there will be one more practical problem. I can tell you what happens when you start calculating a distance and you go for the patrolling of your line. That won't be accurate at all. That will be showing far away from the station that is actually available. That will always give the wrong results.
Yes sir, yes sir, yes sir. Thank you sir, thank you sir.
And with that, I would again say, Pankaj ji, thank you very much for accepting my invitation and becoming the part of that Igniting Power Engineers platform under umbrella of IPE. We can do one session of fundamentals of protection systems and more sessions to come. And I would request you to kindly spare some valuable time and share your knowledge on the different topic. We will discuss and announce accordingly. And thank you everyone for your support. Thank you to all teams. Thank you, sir. Thank you very much. With that, thank you, and we hereby close the session.